A multi-stage rocket engine throttling up to breach orbit, a digital character sprinting through a virtual environment. They appear as different as physical objects can be, yet they are both manifestations of the same underlying logic. The versatility of code allows it to be used for satellite control, mobile gaming, or hospital administration. To manage this range of applications, we have to look at the specific requirements of each task. A software application is defined as a program developed to solve a distinct type of problem. Before an engineer writes a single line of code, they must first classify the software, as that classification dictates the algorithmic architecture of the project. Every piece of software, regardless of complexity, operates on a baseline logic loop: input, process, and output. The variation happens in the middle. The scale of the processing and the environment where that code runs change depending on the category. Understanding software requires looking past the code itself and examining where that code will live and the physical constraints it must survive. We start at the bottom, at the physical layer every program must negotiate with, the bare metal hardware. Directly on top of this sits system software, like Windows, Linux, or Android. Its role is to act as the direct manager of the physical computer. Above that is application software. These are the tools you interact with every day, like Chrome or Word. Applications do not touch the hardware directly. Every command you issue must pass through the system software to get permission. Looking at a memory allocation script, we can see this negotiation happen at the code level. When you try to open an application, the system software first checks the available RAM. It decides if there is enough physical memory to safely proceed. Only after that memory is granted does the application execute its specific task. System software prioritizes hardware survival. This frees the application software to focus on solving user problems. Moving beyond the basic stack, we find specialized categories, like engineering and scientific software. Programs like MATLAB or AutoCAD are built for data simulations. They rely on matrix calculations and processing algorithms to analyze physical structures and forces. Before a launch vehicle ever leaves the pad, engineering software has already calculated the aerodynamic stress it will encounter. On the opposite end of the computing spectrum is software designed for minimal processing power, embedded software. This code runs inside hardware like washing machines, microwaves, and car engines, often operating on kilobytes of memory. Embedded software operates on a state space architecture. The machine exists in one specific state at a time. It only transitions to the next state when exact sensor conditions are met. In code, this translates to an infinite loop, running to maintain control over the hardware over long periods of time. The software constantly pulls physical inputs, like a sensor that reads the water level, and waits for the trigger to advance. While engineering algorithms maximize raw processing power, embedded algorithms maximize stability within hardware constraints. Software is also classified by how it is distributed. Product line software, like Adobe Photoshop or VLC Media Player, is built for a general market. Because the developer doesn't know what machine the user owns, the software must be versatile enough to run locally on millions of different personal computers. Web applications solve the distribution problem by bypassing local hardware differences. Platforms like Gmail or Netflix require zero local installation to function. This is achieved through a client-server architecture. Your local browser is an interface that sends user requests across the network. The algorithmic lifting happens remotely on a powerful centralized server, and only the result is delivered back to your screen. Web applications sacrifice local processing speed to guarantee accessibility, shifting the computational workload off the user's machine. The final category requires a shift from traditional programming, artificial intelligence software. Instead of engineers writing explicit step-by-step instructions, AI software is designed to learn and make decisions based on data. This requires an architectural shift from linear flowcharts to interconnected neural networks.
A recommendation algorithm begins by ingesting data points, such as your watch history and search queries. Rather than relying on rigid if-then logic, the hidden layer processes this data using pattern recognition, adjusting the mathematical weights of different variables. The network synthesizes those patterns to output a prediction for the next video you want to watch.
AI relies on different data structures, tensors, and probability matrices, proving again that the software category dictates the required mathematics. This graph maps these classifications by data volume and computational complexity. Embedded software plots in the bottom left, requiring low data and low complexity, while AI occupies the top right. An engineer uses this map to select tools. Building an ATM requires a different set of priorities than building a multiplayer game. Knowing which category your software falls into defines what you are building. But in the 1960s, programmers discovered that classification did not solve the problem of how to build it at scale. As hardware transitioned to these room-sized IBM mainframes, the complexity of the code required to run them began to exceed what a single person could manage. Even with the correct algorithms, projects began to miss deadlines by years and exceed budgets by millions. Software would crash at scale, even if it worked in a small test. This realization that the craft of writing code was separate from the discipline of managing its production led to the software crisis. It marked the moment when programming had to evolve into software engineering.